In my last video, I proposed that you could make your first Max for Live device in 30 seconds. And although we did end up with a device that worked in just a little bit over that time, it wasn't much of a device. And I glossed over a lot of the things that you'll run into when you actually open Max and start working for the first time. So in this video, I want to go quite a bit slower and walk step by step through making something real, a simplified clone of Live's Chord MIDI device. We'll look at the whole process, from pushing the mystical edit button for the first time to actually finishing and using your device. We'll assume you've never pushed the edit button before, so we'll start from the very beginning and learn some workflow tricks for getting around the interface quickly. Most importantly, we'll talk through the problem that we're solving. We'll look at how to come up with a concept for a device, how to figure out the steps that you need to actually make it, and how to do those steps. Once you get your head around the basic mechanics of patching in Max, the real work is figuring out how to break a big problem down and solve it. So let's go. All right, to start, we want to load a Max MIDI effect from the Max for Live section in the browser. For Max, there's a device type that corresponds to all of the native device types in Live. So Live has instrument, audio effects, and MIDI effects, and Max also has instruments, audio effects, and MIDI effects, the Max versions of those things. Max can do a lot of things that don't really fit into any of these categories. So sometimes, depending on what you're trying to make, the type of device that you choose is kind of arbitrary. In this case, we really do want a MIDI effect because what we're trying to do is take MIDI in, process it, and then spit it back out again. So we have a Max MIDI effect here, and now we push the edit button, which opens the Max editor. And let's blow this up to be bigger. We don't really need to do much in Live right now. And also zoom in a little bit. And I did that by pushing the Command and plus keys. So we can zoom in and out of the interface using Command plus and Command minus. So we have a MIDI in object and a MIDI out object, and they're connected with a cable. And these are also objects. So these are what are called comment objects. You can leave comments in your patch for yourself to help you figure out what's going on. This line here is actually really helpful. This is showing you the bottom of the devices in Live's device view. So you know when you're looking at this that if you need to see something in Live's interface, it needs to be between this line and the top of the screen. For our purposes here, we can just delete these comment boxes. We don't need them. So I'm going to select them and delete them. And also this one here. So we have a MIDI in object connected to a MIDI out object. Okay, before we do anything else, we can grab these objects and move them around because our patch is unlocked. This icon down here allows you to switch between locked and unlocked mode. In locked mode, you can interact with UI elements on the screen, but you can't move them. In unlocked mode, you can move them, but you can't interact with them. So for example, if I create a live.dial object, which is an object that looks like Live's dial, and I try to drag it now, I can't do this. If I switch to locked mode, I can drag the value of the dial, but I can't move it. This is the way Max has traditionally worked. There is this option, though, called Enable Operate While Unlocked, and I leave this on all the time. With this on, there's a little bit of cleverness. In the unlocked mode, if you click on a UI element and drag within it, you can interact with it. If you click on the margins of it, you can move it around. I prefer not to have to toggle back and forth between this locked and unlocked mode all the time. So I tend to leave this Enable Operate While Unlocked option on. All right, so in a previous video, I talked about how making devices in Max is about objects that you connect together with wires. This MIDI in object is connected to this MIDI out object, and if I play notes on the keyboard, MIDI is flowing through the device. So MIDI in Live's device chain accepts the MIDI that comes in the left side of the device. And in this case, we don't do anything to it. We just spit it out the right side of the device. We're going to need to do a little bit more than this to actually make our device, though. But let's introduce the idea of how you create and connect objects. So there are tons of objects which are available in these various menus at the top here. Different types of objects in certain categories, as well as some common ones that are available from buttons here. There's also an easier way to create objects, which is to press the N key, which creates a blank new object, and then start typing. And as you type, Max will fill in a kind of autocomplete for you of what it is that it thinks you're typing. So let's start typing PRI, and that's going to create a print object, which we will enable here. So we can connect our MIDI into this print object, and we can display things in the console. And the console we can open by hitting Command M or Control M on Windows. And now if I play a note on the MIDI keyboard, watch what we see in the console. A bunch of information, and we're not given any information about what this is. There's just a bunch of data. So this is, and when we release the note, we get more data. This MIDI in essentially just takes a raw MIDI input stream in bytes, and MIDI out takes the same thing. So what we need to do is be able to separate out this information in order to make our device. But let's do something before we start working with MIDI. Let's work with some more fundamental objects. So we're going to press I, which creates an integer object. There are two different kinds of numbers in Max, integers and floating point numbers. We need to deal with them slightly separately. If I drag in the integer box, we can see that we're outputting the value of the integer box to the print object, which then displays it in the console here. Let's press I again to create another integer object and connect the top integer object to the bottom integer object. And now when we drag the top one up and down, we update the bottom one. If we drag the bottom one, we don't update anything because information only flows from outlets to inlets, not the other way. So this cable here connects this output to this input. It's not bidirectional. That's an important thing to remember. Let's create another object now by pressing the B key, which creates what's called a button object. And button objects send a special message called bang. And bang is this kind of universal keyword in Max, which tells anything that the bang is connected to do the thing that it does or output its value. So if I press this button to send a bang to this top integer, it'll send the value 19, which we will see printed, and it will update the bottom integer. Right. If we connect bang directly to print instead of to our integer object, it actually sends the word bang. You could send the message bang in any way that involved sending the text word bang. You could create a message box that sends the word bang, etc. All right, so we've built a relatively simple system of stuff here. Notice that we can connect objects to multiple other objects at the same time. So pressing this button now sends a bang to this integer box and to the print object at the same time. We could also even connect it directly down here if we wanted to, which doesn't do anything we can see. Let's do something a little bit more interesting now, which is to do a little bit of simple math. We're going to create two integers here and another one down here, and then we're going to create a plus object, and we'll give this an initial value or an argument of 10. We're going to connect this integer object to the plus 10 and its output to the bottom 10. And now every value that we enter in here will get sent down here. 10 will be added to it, and then the sum of that will be output to the final object at the bottom. So if we enter 5 here, we add 10 to it, we get 15 at the bottom. If we add 50 here, we add 10 to it, and we get 60 at the bottom. Now let's connect the other integer object to the right side here. And so far, we haven't sent it any value. So 10 is still stored as the argument in this object. If we send a different number here, let's say 1 instead, nothing seems to have happened, right? This number still says 10, nothing changed here or in the output at the bottom. But now if we enter new values here, we'll enter 50 again. In the left object, we can see that we've updated the add by sending it a value to the right inlet. And this is an important principle in Max. You can immediately send values out if they're connected to these orange tinged inlets. And you can store new values and then wait for something to come in the left side, with these blue tinged inlets. These are sometimes called hot and cold inlets. And notice that as we mouse over the inlet, we see a little bit of information about what's happening here. So this is a really important idea in Max, that we can store values for use later without showing any change to the output, or we can process input immediately and send it out, depending on which of the outlets we connect to. And many objects have both hot and cold inlets for these purposes, to store data for use later, or to process the data and immediately send the new value out. All right, so this is cool, but it's not a very useful calculator, because if we want to change either of these numbers, we can only get a result if we change the left one. So that's kind of annoying. What we want is a way that we could update the rightmost number, but still bang the output. We do this using a special object called trigger. So if I enter N and press the letter T, we've created a trigger object, which is then waiting for one or more arguments. So what we want is to tell this object to send a bang and an integer. So instead of connecting the right integer box directly to the left input of the plus, we're going to connect it to our trigger instead. We'll connect the output on the right, which is an I or integer output, to our plus on the left side, and send a B or bang out the right side. So how do I know these things? Well, only because I've used these objects before. So I know that the trigger object, abbreviated with a T, takes certain types of arguments which define the type of output that we get. And I know that B stands for bang and I stands for integer. I could add additional arguments here. I could add an F, which creates an additional outlet, which sends a floating point number instead. And so if I connect, say, a message box to this and change this number to 21, we get a 21 with a decimal point after it. And we've sent 21 here and a bang here, which means we've updated the internal value of this to 21 and triggered the calculation. So 70 plus 21 equals 91. And so now if I change either side or either of these integer boxes, we tell the plus to send an output. So what we've done here is we've used the trigger object to allow either of these integer boxes to update the calculation. We first send the output of the integer, and then we send the bang. And this is an important principle in Max, which is that data flows from right to left. If we have an object that has multiple outlets, the data flows from the rightmost outlet first, and then through the outlets to the left. And this is really important because while Max does things very quickly, it does them one at a time. And so often you're looking at something and you think that it's happening instantly, but in fact, every single piece of data that flows through the system is flowing through one piece at a time and in a specified order. And that order is determined generally by the outlet order of the objects that things are connected to, and then the order in which they're connected to each other. But this can cause real problems. So let's create another little simple patch. We're going to create two integers here, another integer here. We're going to connect both of them together, and then we're going to create a button at the top which sends a bang to both. Now, if I enter the number 10 here, what's going to happen? Well, we'll see 10 at the bottom. And if I enter the number 50 here, we'll see 50 at the bottom. Now, if I press the button, what do we expect to see? Let's set this to something else, like something random. If we press the button, what do we think will happen? Let's try it. Well, it looks like 50 is in the bottom. But what actually happened is that we sent 10 first and then immediately followed it with 50. Okay, cool. How can we prove that to ourselves? Well, let's create a print and send the output of both of these also to print. We'll stick the print in the middle, just so it's sort of easier to follow. Let's clear our console by pressing the X at the bottom and press the button again. 10 followed by 50. And that makes sense with what we said before, that data tends to flow from right to left. Now, there's a real problem with this though, which is that there's only one outlet here that's doing this work for us. So the way that it decides what's right and left is based on the physical position of the objects on the screen. This is pretty dangerous because if we reorder the objects visibly on the screen, we've completely changed the patch. Now, 50 will come out before 10. We get a different result, a different apparent result at the bottom, and we see that 50 is coming out first in the console. This is potentially dangerous because anybody could open up your patch, move a couple objects around, and expect that because this is a thing that's wired together, it's going to behave the same way as it did when you saved it. But that's not the case. So in order to defend against these kinds of problems, we can use the trigger object again to make sure that this doesn't happen. So the way we would do this is to create a trigger with 2 bangs, and instead of connecting our button directly to the 2 integer boxes, we'll connect it to the trigger and then send the bangs out there. And now the order of the objects on the screen doesn't make any difference because the outlet ordering overrides it. So here we'll get 10 followed by 50. And even if we move these to absurd places, we'll still get 10 followed by 50. So this is a way to defend against the possibility that the physical position of the objects on the screen changes what's happening in the patch. All right, let's switch gears for a minute and take a look at Live's Chord device. We'll turn the max MIDI effect off for a minute, and we'll study this device a little bit and try to figure out how it's doing what it does. So the way the Chord device works, we play MIDI input, and then we have 6 possible additional notes that can be added to that MIDI input. So if I add, say, 3 here, we've added an additional note 3 semitones above the note that comes in. So if I play middle C, we get middle C and E flat out. And we can look at the MIDI monitor and see that that's true. All right, it says D sharp, but D sharp and E flat are the same thing for the purposes of this exercise. We also have a velocity control here, which scales the incoming velocity between a range of 0.01 and 2 times the input velocity. So if we set this to 2 and we play in a note, we can see that our initial note was 119. 2 times that is, I don't know, whatever that math is, but it's more than 127, so the value's been constrained to 127. Notice that when we release, and that sends a velocity of 0. We'll play a little bit softer now. 26 times 2 is 52. Okay, fine. If we set 0.5 as the value here instead and play a note, 26 was our input volume, divided by 2 is 13. So we can see that this is a multiplier of velocity, and this is an adder of pitch. And now we have a pretty good idea of what we need to do to reproduce a device like this. A note will come in, it will have a pitch and a velocity, and then we need to add some number of semitones, either up or down, 3 octaves, or 36 semitones up or down. And we need to multiply the incoming velocity by the velocity scalar. And then the rest of the controls in here are just 5 more copies of that thing. So we can have up to 6 additional pitches. The pitches are added to the incoming pitch, and the velocity is multiplied by some factor here. That's all we need to know to build our chord device. Let's go back to our Max editor and actually make this thing. We have MIDI input connected to MIDI output. What we want to do is filter out the notes from the rest of the MIDI stream. If I move my mod wheel, we will still send data through the MIDI in, which we want to get to the MIDI out. And we can prove that that data is coming in by attaching the MIDI in to a print object and moving the mod wheel. So now I move the mod wheel, we can see it's sending huge streams of data. If I move the pitch bend wheel, it does the same thing. We want all of that data to go through unaffected. If I play notes, we want those to be processed in some way. So what we need to do is separate the notes from the MIDI stream. And there's an object for this called midiselect. So we start typing midiselect. And again, the reason that I know the existence of these objects is not some kind of magic. It's just because I've built devices like this before. Learning a collection of the objects is part of what you need to do to build stuff in Max. It's not a miracle that I know these things. It's just that I've done this before. We're going to connect our MIDI in to the MIDI select here. And now what we can do is we can provide what are called attributes within the text field of the box to determine what types of MIDI data get filtered out. So we type the @ symbol and we type note all, which is a kind of special code that says the MIDI input stream that comes in here, separate the notes out and send them out through this outlet, and send everything else out through this unselected raw MIDI data output at the bottom. Now, we're still going to leave our main cable connected from MIDI in to MIDI out because we want whatever we do, we want to simply go to MIDI out no matter what, including the first note that we play. We're using MIDI select here just to generate our new additional notes. So now we know that we know this because we can mouse over it and see this outlet will spit out note on and note off information, and it says after it list, pitch, and velocity. Well, let's connect a print object to this and see what happens. So I'm playing middle C. Okay, and as I hold it down, we see that there are two numbers. And as I release it, we see two numbers again. The first number is the pitch, and the second number is the velocity. So a note on has a pitch value and some velocity between 1 and 127. A note off is the same pitch with a velocity of 0. This is how MIDI communicates. Integers greater than 0 between 1 and 127 represent a note on with a given velocity, and a velocity of 0 means turn that same note off. So what we need to do is process the pitch and the velocity separately, right? We need to do two different things with that. Before we do anything else, let's actually just bundle this thing back together so that it produces a valid note coming out. So there's an object for this called midiformat, which is essentially the output version of MIDI select. And it has an inlet here, which corresponds to the outlet we have here. So we connect that outlet to this inlet, and then the MIDI message output will connect to our MIDI out. And right now, we're just going to send two versions of the same note for each note, right? One that just goes straight down the pipe here, and one that gets split off, filtered through MIDI select, put back into a functional MIDI message via MIDI format, and then sent out. Doesn't sound any different because we're sending two identical notes. But this connection here is the one that we want to break and do something interesting to. And what we want to do is, like I said before, process the pitch and the velocity separately. So we need this list of numbers turned into two separate numbers that we can manipulate. There's an object called unjoin, which is specifically for taking in a list and splitting out the elements in the list so that they each come out a separate output. Unjoin can take an argument. Let's say we give this 10, and that will change the number of outlets. In this case, we only need 2. There's always an additional outlet, which is an extra outlet beyond the number of arguments that you give it. And if you don't give it any argument, it defaults to 2. So we'll connect our MIDI select here, and now we should get pitch out this side and velocity out this side. Okay, this is a good time for an important philosophical aside. At the moment that the numbers come out of the output of MIDI select, they're not MIDI anymore. They're just numbers. This is generic, meaningless data that you can fling around inside your Max patch and do whatever you want with. It's only MIDI again when we pack it into something that looks MIDI-ish and send it out the MIDI out, which means that we have total freedom to manipulate these numbers inside our Max patch. Well, why is that interesting? Because the numbers that we want to work with, once we've detached them from their origin, they become much more flexible and much more powerful. Also, it's our responsibility to format them the right way to do the things that we want them to do. But imagine if you wanted all of your pitches in your piece to come from your latest blood pressure readings, and you wanted all the velocities to come from the average annual rainfall in Detroit, Michigan. That kind of thing is easily doable in Max, and it's essentially impossible if you're only working with MIDI data. So it's an important principle in Max that we quickly separate data from its origin, and then we can manipulate it in any way that we want inside the machine. There's a great article from David Ziccarelli called Communicating with Meaningless Numbers that talks about the importance of this kind of generic representation of data. Okay, aside over, let's do something interesting with these numbers now. Let's connect two more print objects to see what kind of data we're getting here, to prove to ourselves that this is real. So if you give an argument to the print objects with a name, then we see that that data is tagged with that name. So if we play a note now, we see velocity of 92, pitch of 60. Why does velocity come first? Well, because it's the rightmost outlet. And again, the data always flows from right to left. If we have an object that has multiple outputs, the data comes out outlets to the right before it comes out outlets to the left. When we're done doing whatever it is that we're going to do to this unjoined data, we're going to need to join it again. And as you might imagine, there's a corresponding object called join. You can also give it some number of arguments that determines how many inlets it has. It combines all that data into one list and sends the list out its outlet. We're going to want to send that back to MIDI format. Okay, so before we connect the outlets to the inlets, we need to do something with this data, right? Let's move our object over. We need to add to the pitch. So let's do that. We'll create a plus again, and let's just say 5 for now. We'll connect the outlet here to the inlet on the right side, its outlet to what we're saying is the pitch input, and we'll just connect the velocity directly because we're not doing anything to that. And now when we play a note, what we should get is the note that we play sent down this pipe, and a note, a perfect fourth or 5 semitones above it, sent out this contraption here. And that's exactly what we get. And if we go back to live, we can put our MIDI monitor after the max MIDI effect to determine that that's true. Let's clear this, play a C. We should see a C and an F. And right now the velocities are identical because we haven't done anything to velocity yet. That's essentially all we're doing. Let's clean this up and make it look a little neater here. Different people have different ways that they like to make their patches look neat inside or not neat if messiness is your thing. I try to make it so that the objects are flowing in straight lines as much as possible. All right. If we want this to be a different interval instead, we can change the argument in here. But wait a second, that's kind of lame. We don't want to have to change the argument. It would be much better to do this with a dial, which is the thing that we're using in Live to do the same thing. And there is a live.dial object. And if we connect its output to the input here, then we can make changes to the stored value, which will then wait and update when we play a new note. So if we change this to 7, new notes are played and a new note, a perfect fifth above. If we change it to 11, we'll get a major 7th. Okay, that's working. Essentially, this is doing what the thing in Live is doing, but the range is kind of silly. It goes from 0 to 127. And what we want is for it to go from -36 to +36. And this is where we need to introduce the notion of the inspector, which is a way that we make changes to the behavior of the objects within our patch. So to open the inspector, we select the object we want to work with and we hit Command-I. I think this is probably Control-I on Windows. And in the inspector, we have tons of different options for how we can change the way this thing behaves. We can change how it looks, we can change its size, we can change the values that it can send out. So what we want for this is a bipolar knob, right? So if we look back in Live again, we can see that these knobs have a little triangle at the top. That's what we want in our patch. In the display triangle, we select this box and now we have the triangle. It's not still the wrong range, but we're getting closer. If we scroll down in the inspector, there's a lot of stuff in here. You can see that we can change the range here, and it's currently set from 0 to 127, but we want it to be -36 to 36. Now, we can see that this actually shows the right values. There's a little bit more we want to do here, though. We want to specify a unit style for this, which in this case is semitones. This will give us a unit. So it's not actually changing the values that come out. It's just changing the way the thing looks. And the other thing that we might want to do here is change the name that we see. So in Live, this is called Shift 1. We'll change that to Shift 1. Each of the shift knobs from 1 to 6 has a separate number, so we'll change that. All right, let's talk a little bit about velocity. We know that velocity comes as part of a list from our midiselect, and in the unjoin object, that number that corresponds to velocity is sent out this outlet. So we know that this is the place where we need to isolate it and change it. We looked at the Chord device earlier and we saw that the velocity control scales the incoming velocity to a range between 0.01 and 2. So we multiply the incoming velocity by the number that's set in that range. There's a couple things that are a little bit tricky about this. We might end up with fractional values, numbers that aren't integers, and we might end up with numbers that are smaller than 1 or greater than 127. But we know that velocity needs to be an integer between 0 and 127, and that anything other than 0 should be at least 1. So we shouldn't have numbers between 0 and 1. It's not clear what will happen if we try to deliver weird numbers like that to a synthesizer. It might work, it might not. Probably a good idea would be that we format the numbers correctly to make sure that wherever they end up will be processed correctly. So what do we need to do? We need an object that looks kind of like the one that we have in our Chord device, which is an object in Max that's called live.numbox. So let's create one of those, live.numbox. And this looks like it's the wrong range and it doesn't have our little triangle. So we can fix all those things in its inspector. There's an option here, display style triangle. Okay, so now it has the triangle and we need to set its range between 0.01 and 2. All right, well that's closer, but it's not quite right because it's displaying as integers. So we need to change the unit style to float. And now it goes from 0.01 to 2. We will attach this to the cold inlet of a multiply object to set the amount that we multiply by. And then let's detach our unjoin from there and run it into here. Oops. And then connect that back to the join here. And let's give ourselves a little bit more space here. Do a little bit of UI adjusting just to make this thing look a little bit more manageable. Okay. Good. All right, so there's going to be some problems with this. I'm deliberately doing this in a way that's not going to work, and we'll see why in a second. So we play a note, and we don't hear anything. Well, we haven't set a cold value yet. First of all, we know we want the default for this to be 1. So we can say that we want the initial value of this to be 1. Enable initial, 1. There we go. And now when we double click it, it should jump to 1. That's what we want. Okay, all is okay so far. The incoming value here is 88 multiplied by 1 should give us 88 coming out the other side, as we expect. Now, what if we set this to 0.5 instead? We'll play a note, 109. Well, what's half of 109? It seems to be 0. Why is that? Well, the multiply object has, by default, expects integers and is going to multiply by integers. We need this to multiply by a floating point number. So we need to give it an argument that contains a floating point number to prepare it for that. So now, if we set this again, we need to feed the cold input once. 109. Oh, I happened to play exactly the same velocity that time. 109, and half of 109 is 54.5. So that's okay so far, except we're eventually going to need to turn this back into an integer. Let's set this to a really low number, 0.01, and play a relatively quiet velocity. So the incoming velocity here was 38. times 0.01 gives us 0.38 coming out the other side. Well, that's not going to work. Any number greater than 0 needs to be at least 1. We need to make a split here. We need it to be able to process 0 because an incoming velocity of 0 is what we need to turn our notes off. So we need for zeros to become zeros and anything greater than 0 to become at least 1. So we need to test our number that's coming in and send it out one of two possible outlets. And there's an object that can be used for this called routepass. And what we'll say is routepass 0 with a dot because we want to pass either 0 or any other number that comes in. So what we'll do is we'll say the output of this, instead of going directly to join, will go to this routepass 0. The left outlet will get our zeros. And let's test this by attaching a couple of message boxes in here. Out of the right outlet, we'll get anything that isn't 0. So 0.26 there. And when I release the key, we should get a 0 coming out of this cable. Right. Perfect. Okay, that's doing what we want it to do. So now we know that our zeros should just be zeros. The one last step for it is that we want to convert these into integers rather than floating point numbers. So what we can do for this is use our old integer. And if we feed this thing a number, it will turn that number. If we feed this thing a 0, it will just turn that 0 into the 0 without the dot. So we can prove this to ourselves by playing another note, releasing it. We see that by mousing over the cable here, we see that we get a 0 dot. And out this one, we get plain 0. Oops, I didn't want to attach it here. I wanted to attach it here. So now our note offs at least should work. We still have a little bit more work to do to our note ons though. What we said before is that any number that's greater than 0 needs to be at least 1 and should be no higher than 127. So we need a way of constraining the range of the numbers that come out of here. And there's an object for this called clip. And we'll say clip 1 to 127. So what this will do is take our input and make sure that it is no lower than 1 and no greater than 127. And let's see what we get now. So our number coming in was 0.88. That gets rounded up to 1. It doesn't really get rounded up. We'll cover that in a minute. Play another number, 1.22. So that's fine. That's above 1. So it's within our range here of 1 to 127. We'll feed this a big number now. We'll say 2. We'll play loud. The number coming in is 246. Well, that's way too high, but it gets clipped to 127. So now both our zeros and our numbers are more or less doing the right thing. There's one more thing that we need to do though, which is that we need to make sure that the numbers that come out of clip eventually become integers. So let's give us 0.5 again as our velocity input. And we can see that we're getting numbers out of here that are not integer values. So what the obvious answer would be, can't we just run this output into our integerizer? But this doesn't quite work because if we do this, we end up just chopping off everything after the decimal point. So if we give it a complex number like this, and we run this into the integer, let's give this something that's going to give us weird numbers. Right, so 45.87 here should round up to 46. Instead, the integer just lops off everything after the decimal point and turns it into 45. So what we need to do is round appropriately. And for that, there's an object called round. And if we don't give it any arguments, it does what we want here, which is to round up if things are over 0.5 and round down if they're below it. So let's see what number is coming in here. 46.69 is the number that came in because the velocity that came in here was 115 times 0.41 turned into 46.69, which rounds up to 47. So now this is doing what we want. So let's clean this up a little bit and then we can talk about exactly what's happening here, because it's quite a bit of stuff that we've done here to make this work. More than you would immediately think should be necessary. All right, so what did we actually do here? We multiply the velocity by some number between 0.01 and 2. We split off our zeros and immediately turn them into integer forms of 0. And then for every number that's greater than 0, we smush it to a value between 1 and 127, and we round that number up or down as necessary, and then convert it into an integer. And now all the incoming velocities should be scaled properly and should turn into a valid velocity value, an integer between 0 and 127, but nothing between 0 and 1. That seems like a lot of work, but remember that you have a lot of flexibility with this data. You might not want these numbers to be velocity anymore at all. You might want them to be some arbitrary other data with some completely different range and scaling. In this case, we want to manipulate the velocity, but then turn it back into valid velocity values, which is why we need all of this plumbing here. Okay, so we've done all this stuff now, and we're in pretty good shape. There are two very big problems with this patch, which are not immediately obvious. One of them is that if we change the shift value while we're holding down a key, the note will never release. Let's give ourselves a little bit more frequency here on our cutoff so that the note never actually dies while we're holding it. So I'm going to hold a note, and then I'm going to change the shift value from 3 to 5. Now, when I release the note, what do we think will happen? Let's think about it for a minute. Then I'm going to release the note. No hands. So what happened is that our original note, the C that we played, was released. The E flat that was generated was not released. And let's think about why for a second. First, I'm going to turn off this annoying noise by laying my arm on my keyboard, which will override the polyphony. Okay, that should turn all the notes off. So the reason for this is pretty simple. When we play our C, we generate a note 3 semitones higher with some positive velocity. To turn that note off, we need to also send a value of 63, in this case, with a velocity of 0. But before we can do that, we've changed the 63 to a 65, right? So when the velocity of 0 comes in, it's now bound to a different pitch. So the 63 that's sustained never gets a 0. This is actually kind of a challenging problem to solve, and it's going to be beyond the scope of what we want to do here. Live does this in a really elegant way, which is that if you turn the knob while a note is sustained, it doesn't do anything to that pitch until you release the key, and then it releases the original pitch and waits for a new note to be played on that pitch before it creates the new transposition. This is beyond the scope of what we want to do here, but let's solve this in a simple way. There's an object called flush, and flush takes in pitch and velocity and outputs pitch and velocity, so it can just kind of go right before our join object here. And we'll use this as a kind of intermediary before we get to our join. And when flush receives a bang, it just sends a note off for any note that hasn't gotten one yet. All we need to do for this brute force solution is make it so that every time we turn this knob, we trigger a bang, which then is triggered to flush. So we'll create a button for this, and we'll attach a cable here. I'm not too concerned with where the data gets to first, because by the time it has created the note that's a problem, it will instantly send the bang afterwards, so it's not a big deal. So if I hold a note down now, we get a transposed version in addition to the original version. If I turn the knob, we flush the note that's been generated, but note that we don't remove the one that we're playing manually, because that's coming down this cable here. Only the generated note needs to be flushed. This is not an elegant solution to this problem. A better one would be to do something like what Live does. This is beyond the scope of what we want to do here. Okay, the other big bug here is that if shift is set to 0, we would expect nothing to happen. This whole circuit should be bypassed. But in this case, that's not what happens. We generate a second copy of the incoming note, just a tiny fraction of time later. Which means that if we set our velocity scaler, for example, to 0.01, and we play notes, we can't really hear much. Because what's happening is we're immediately sending another copy of the incoming note with a velocity of 1, which cuts off the original note. We can look at our MIDI monitor to prove that this is happening. I play a C. What we see is a C with a velocity of 123, immediately followed by a C with a velocity of 0, immediately followed by a C with a velocity of 1. And the reason for this is that we're trying to play two notes at essentially, but not exactly the same time. The second one cuts the first one off by sending it an implicit velocity of 0, and then plays itself with a velocity of 1. The result is that we don't hear anything. Live's chord device is much more clever than this. If you set a knob to 0, that whole shift option is disabled. And if you set a knob to any value that has already been set somewhere else, for example, if we set this to 2, and then set this one to 2, it automatically disables the second knob. This is much smarter behavior, but it's beyond the scope of what we're going to try to do here today. So we just have to live with these two bugs for now for our simplified version of this patch. So all we need to do now to create a complete version of this chord device with the bugs in place is create 5 more copies of all of this nonsense here. That looks like kind of a lot to think about. So there's a way that we can do this that makes it a little bit easier. We take everything except our UI elements, because we don't want to think about those. Everything that's specific to this portion of the patch. So everything between the MIDI select and the MIDI format, except for the UI parts. We go to the edit menu and we choose encapsulate, and watch what happens. All of these bits go into a single object, and we can adjust the positioning of this object a little bit so that it's nice and clean. Let's move the UI elements around slightly. Doesn't need to be this big, and we can call this one shifter or something like that. Right, and all the work I did on fixing the UI is now screwed up. Okay, so what exactly does encapsulation mean? Well, essentially we're taking all of those objects and sticking them inside another object, which is itself a patcher. This object is called a patcher or a sub-patch. And if we double click on it and open it up, we can see that all the stuff that we built is inside. This is a nice way of sort of organizing a bunch of work that you've done into a logical box. And so now all we need to do to make 5 more copies of this is duplicate these 3 things 5 more times and then wire them back up. So I'm going to do this super quickly now so we don't have to look at all of the work that's done, but we'll just do one for now slowly and take a look at what that all means. One thing we do need to do here is change the name of this thing. So let's call it Shift 2. And we need to connect the MIDI select to its input, and we need to connect its output to the input of MIDI format. And now we should be able to create 2 pitches instead of just 1. Let's make a minor triad. So we have an incoming note, and then we generate another note 3 semitones higher, and another one 7 semitones higher. And we just need 4 more of these before we have a complete clone, simplified clone of the chord device. So I'm just going to do that super quick. All right, we're back. This looks a little bit sloppy now, but we have 6 copies here, and we've numbered them 1, 2, 3, 4, 5, 6, and we've built a big chord out of them. There's one other bit here that we haven't really done yet, which is that this thing looks like a mess, and what we want it to look like is Live's chord device, which has 6 knobs and 6 velocity sliders and nothing else. What we're looking at here is a big pile of wires and a bunch of objects that we don't actually need to see. All we really need to see are the knobs and the sliders. Well, Max has a notion of a UI environment, which is called the presentation view. What we're looking at right now is the patcher view. And if we go to the presentation view by clicking on this icon here, we see nothing. And the reason for that is that we have to specify which objects we want in the presentation view. So we'll select those, and then we'll open the context menu and say Add to Presentation. And then we'll select these and do the same thing. And you can see once we've added objects to the presentation, they get this little red ring around them. Now, when we switch to the presentation view, everything that wasn't added to the presentation goes away. And we can change the layout of these objects independently in the presentation from the patcher. So we can specify a completely different arrangement of presentation-enabled UI objects between the two views. So now I'm going to quickly, again, jump ahead, and I will have sorted all of these to the right places. All right, we're back. You can spend a lot of time very carefully aligning these objects with each other, but the important thing is that we get them roughly where they're supposed to be. Now, if we switch back to the patching view, we can see the objects snap back into place. We see the cables again, and we see all the other objects that haven't been added. And then when we switch to the presentation, we get our special designed UI. The one remaining thing to do, and really the only remaining thing to do, is to define that we want our patch to open in the presentation view. And just like we had an inspector for objects, there's also an inspector for the patch itself. So if we don't have an object selected, the inspector gets this little P button, and that's where we specify this. There's lots of things we can specify here, but one of them is open in presentation. And now we see our little divider line, which shows the absolute bottom of where we can put the UI objects in order for them to show up. We're below that, so we need to scoot our stuff up a little bit so that it fits in the UI. Otherwise, the stuff will be off the screen in Live, and that's not what we want. Move these all a little bit closer. Looks pretty good now. I am not a great UI designer. These things aren't particularly even, but they do all fit. And now we can save this. And once we save it, we give it a name. Let's call this Chord device. Well, we'll just call it Chord. And when we close the editor, there it is. A somewhat hacky, simplified version of Live's chord device. They should do more or less the same thing, with the caveat that there are certain bugs that we've established we're not going to solve for today. But this is a look at how to clone a native Live device using Max for Live, and it's a pretty good introduction to the basic mechanics of working in a Max patch.